Question 28. Find all solutions to the heat equation. This is heat equation, and the endpoints are set to 0, and you want to find the solution that's of the form of the product of a function of x and function of t. Because the full solution of the heat equation is very long, on the exam I might have questions set up like this where you don't solve the full thing, but you only do the part of it done. So here you recognize this as the separation of variables method, where you look for these type of solutions. When you solve these, you should definitely make sure that all your logic is correct. So you have to say the correct words at certain points to clearly say that you understand what you're doing. Okay. Alright, so we're trying to find the solution of this form, and because we have to plug this u into this equation, we have to calculate du dt, which means you're differentiating only by t, so only this one gets differentiated, whereas when you differentiate twice in the x, only the x part gets differentiated. Now plugging this onto the left and this to the right, this is what you get, and the key thing here is that you should always divide by k times x times t. Okay. Sometimes this k could be given as a value, so it could be like 0.1. In that case, you have to divide by 0.1 x times t. So anyways, you divide this and you end up with this, and the crucial thing to write here is that the left side is a function of t, right? And then this one is a function of x. And because you have a function of t equal to function of x, the only time that could happen is when they're both equal to a constant function. Okay. If the left side depended on t, but the right side has no dependence on t, then there's a contradiction, right? So we know that this doesn't depend on t, but what's a function of t that doesn't depend on t? It means it's a constant function, right? And another trick is to put this constant as negative lambda, because if you do, then taking this, multiplying by x, and moving lambda x to that side gives you this well-recognized form, which we solved before. Okay. Now, in addition to this, you have the boundary conditions, right? The boundary conditions. When you plug in x as 0 for various t, so if you plug in x as 0 and set this equal to 0, then you end up with the following case. X of 0 t, it should be 0, and also when x is 4, it should be 0. And if you had t of t equal to 0, but because u is x times t, if t of t was 0 for all t, then u will just always be equal to 0, which means it's a trivial solution. So you don't want the trivial, therefore you're forced to have just these two equal to 0. So we have this. But then look at this. This is endpoints, and this with this equation, that's something that you have solved before. Actually, it's question 23, and it's part A. And so we can quote that result and write it as this. We know that this is true actually for n from 1, 2, 3, and so on and so on. Okay. We also solve the first one to get t. So this equation here, this one, we can solve this for t of t, and that's a separable equation, so it's very easy to solve. If you solve this with this lambda plugged in, if you solve this, this is your t, and now putting them together, if x and t is multiplied together, then you end up with this. Okay, and see, I just put c prime times c as just a constant. It's just some constant, so I'm just putting it as c. So that's your solution. And here, n has to be a positive integer. In other words, n has to be 1, 2, 3. Okay. If n is one of these values, then this is a solution that is of the form of function of t times function of x multiplied together. Now, similarly, we have another equation very similar to the previous one. The only difference is now you have the endpoints, its x derivatives equal to 0. And I told you that this is called the Neumann condition, Neumann boundary condition. When the derivative is fixed to a value, that's a Neumann condition. And that's same as having the boundary as insulated. If this is 0, that means there's no change in the temperature at the boundary, and that's because it's insulated at the boundary. Okay, again, the same story. You plug them in, divide by kxt. This time k is 3, so you have to divide by 3 times x times t. So that's the result, and the same reasoning. Left side is a function of t, but the right side doesn't have any t there, so that means it's a function of t which doesn't depend on t. What does that mean? That must equal to a constant, and we call that constant as the negative lambda. And then you solve this you multiply this over to the other side, move it, then you get this very familiar equation. And again, the boundary conditions end up being x prime of 0 equal to x prime of 5 equal to 0. And this here, these bold-faced words are very important. You should always include them in your solution, okay? Because otherwise, if you have t of t equal to 0, then you end up with a trivial solution. So you can't have this equal to 0. That means the other ones have to be 0, so you're forced to have this. So, and then this is again something that you've solved before, so you can quote the result from before, and then also using this lambda to plug into the first equation here, lambda replaced by that n squared pi squared over 25 gives you this, which can be easily solved to this. And see, it's a separable equation, right? 3n squared pi squared over 25. So if you integrate both sides by t, then this is ln of the bottom, and that's negative 3n squared pi squared over 25 plus a constant, and then you raise it to the power of e so that these cancel. So t is this, and e to the c can be brought down here as a c tilde. You've seen this before, right? Okay, so so this here is the solution for t, and multiplying these two together you get this, where n is a non-negative integer, which is same as saying n equals to 0, 1, 2, 3, and so on and so on. Number 29. Now here's another interesting take of the heat equation. This time you're given the uxt as this form, where as you can see it's a function of t and function of x, right? And all you have to do is just verify that this is indeed the solution to this equation, which is not that hard. All you have to do is just compute it explicitly. So in order to plug into the left side, you take this and differentiate by t, which means you're only differentiating this part. So this coefficient comes out in front. That's what you have. And when you differentiate twice in x, you have to differentiate cosine n pi x twice. Differentiating cosine twice gives you negative cosine. And each time you differentiate, because of the chain rule, n pi comes in front. So n pi times n pi gives you n squared pi squared. So this is what you get. And then if you plug this to the left side, if you plug this to the right side, and compare both sides, they're indeed the same, right? So heat equation is indeed satisfied. Now what about this, the boundaries? Well, if you differentiate once by x, cosine differentiates to sine, right? Then sine of 0 is 0 and sine of n pi is 0, therefore the boundary conditions are met. And then finally, when you plug in 0 into t, e to 0 is nothing, and you get cosine n pi x, therefore that's the solution. So this was a very simple question. All you had to do was to know how to differentiate and plug in values to a function. That's all you had to know in order to solve this. Now, however, this second part of the question is more interesting. See, we know from the first one that it's e to the negative n squared pi. Okay. So we know that e to the negative n squared pi squared k t times sine n pi x, actually, sorry, cosine n pi x is the solution in the case when you had the initial condition as cosine n pi x, right? Oh yeah, I wrote it here, right? Okay. But what if the initial condition is changed? So everything else being the same, everything's same. The only thing is the initial condition is changed. Well, I know that for this to appear, we need this to be 1, right? Because it's cosine 1 pi x, right? And for this to appear, cosine 7 pi x, you need this to be 7. So 7 squared is 49, 7 pi x, that's what you need. And then because the first two is linear, we observe that when solving heat equation using method of separation of variables, we observe that when you just look for the solutions of these, that looks like a function of x times function of t, then when you get those solutions, you can take linear superpositions or linear combinations of the solutions and get the solution in general, right? And same thing here. You can take this one, right? This one, and you can also take this one here. Here. You can take this one and this one, and take 3 times this to make this one work. Take -2 times this one to make this one work. And adding the 2 will make you satisfy. This will make the function satisfy ux of 0 equals to exactly 3 cosine pi x minus 2 cosine 7 pi x. And you can check that because these are individually solutions of the first two, again, taking the linear combinations will still satisfy the first two. So this here is a solution that satisfies 1, 2, 3, all of them. And what you can say after this is because of uniqueness and existence, right? Uniqueness and existence of solutions, you can say that we know that there's a solution, and we also know that if you find a solution, that's the only one. And since we found the solution, that's the only one. And that's how we can solve this. This actually bypasses a lot of things that we had to do. See, what we are supposed to do in the full separation of variables, if you weren't given part A and you didn't know how to use it in this way, you actually had to first figure out that the solutions looked like this for various n values, n from 0, 1, 2, 3. And then once you have this, then you had to use the Fourier cosine series of this in order to figure out the coefficients, right? The reason that this solution was so easy was because, if you think about it, this is already a cosine series, isn't it? It's already a Fourier cosine series with a0 equal to 0, a1 equals to this 3, a2 equals to 0, and a7 is -2. So a7 is -2, and a8, a8, all the other ones are zeros. So other than a1 equals to 3 and a7 equals to -2, everything else is 0. So that's already a Fourier cosine series. And since you're already given a Fourier cosine series, we can bypass that part where you have to calculate the Fourier cosine series. That was why this solution could be written in such an easy way. Okay, here another verification question. You're given the solution and you have to verify that this satisfies the first two, and also you have to it says if it satisfies the heat equation. So we are assuming that it satisfies all of them, okay? And actually it satisfies the first two. You can check. The only thing that's not so sure is whether it satisfies this thing here. And if you plug in t equal to 0, then because e to the 0th power is 1, this means e to the -n² pi² kt over 9, that's what it means. And since you plug in t equal to 0, it leads to the 0th power, so this entire thing becomes 1, and you end up with just this. And because this is equal to 3 minus x, you see that what you need is, you have to do the cosine series. Okay, so you have to do the Fourier cosine series. You use the formula an 2 over L 0 to L of f of x cosine n pi over Lx dx. That's the formula that you use for Fourier cosine series. Now, what is our L? Well, if you compare this n pi x over 3 with this one, L is 3, right? This L is 3. So we set L as 3, and we compute A0 and AN separately. So A0 can be computed by using this formula right here, right? But there's a difference here. C0 is not equal to A0. This is A0 over 2, because if you recall the Fourier cosine series, the formula is A0 plus sigma n from 1 through infinity of AN cosine n pi x over L, right? So what was supposed to be A0 over 2 is now taken by the C0, so these two are the same thing, so that's why I have C0 equal to A0 divided by 2, and if you compute this simple integral, you end up with 3 over 2. And then over here, you just, for Cn is same as An, so Cn is An, so you use this formula, and this is something that we've done over and over again, so I'm sure you know how to do this one. So you get this, and that's it. You got the question was find all coefficients Cn, and we found C0 and we found Cn. Now the second question is find the function f of x, and you take t to infinity, and explain what this means. Well, what does that mean? If you have e to this power and you send t to infinity, that's like e to the negative infinity. But what is e to the negative infinity? That's 1 over e to the infinity, and e to the infinity is infinity. So 1 over infinity gives you 0. And because this all goes to 0, in the sigma you end up with just zeros everywhere, and the only survivor is C0, and we know that C0 is 3 over 2. Okay, and so that's the limit. Well, what does this mean? Well, in order to answer this, you have to go back and think about what this question is, what this heat equation is saying. This heat equation is saying that initially you have a rod of length 3, and 3 minus x means the temperature is like this. The left side has 3 initially and 0 on the right. That's the temperature. 3 degrees on the left, 0 degrees on the right. It's a straight line. That's the temperature distribution. And here, because you have the derivative set equal to 0, that means the endpoints are insulated. If the endpoints are insulated, there is no heat loss at the endpoints. And what you end up with is like the heat gradually becomes average. So places where it was lower than the average temperature will go up. Places where it was higher than the average temperature will go down. And at time t equals to infinity, very, very long time later, the temperature distribution on the rod will be same everywhere, right? And therefore, you will expect to have a constant function when t is sent to infinity, and that is what you're that's what you're getting here. This is a function of x. See, if you send t to infinity, t goes away. You're basically plugging a value into t, so you end up with a function of x. But this function is a constant function. It ends up not depending on x at all. And if you think about what this value is, this is actually exactly same as the average value. If you take a function, integrate over the interval, and divide by the length of the interval, that's called the average of f. Okay, and since the function is defined from 0 to 3, if you integrate this and divide by 3, you end up with exactly 3 over 2, which is same as C0. Okay, so the meaning of this is that it's the average temperature. All right. Question 31. Solve the heat equation. Oh, so this one is where you do everything from the beginning and the end. And it could be that this could be coming in many different parts. See, if you look at this, you'll see that this step 1, for example, is same as question 23. Almost same as 23. So this could be like one question done previously where you can use later. So this question 31 is a very long problem, which on the exam could be divided into many different parts. Okay, so let's try this. So step 1, first you look at this boundary condition and you solve the corresponding endpoint value problem with eigenvalues and eigenfunctions. So since the value of the endpoints are set to 0, so we set the value of the endpoints as 0 from 0 and 2. And then you solve this like before, since this is same as question 23, other than instead of 4 over there, this is 2. So it shouldn't be anything different. So I'm going to skip this calculation, but at the end of the day, this is what you get with n being 1, 2, 3, and so on and so on. Okay. Now, step 2, you have to do the separation of variables. You set u as a product of a function of x times function of t, and when you plug this in, you end up with this. So you plug this into the heat equation here, and you end up with this equation, and you always divide by k times x times t. So that's what you're getting. And then the same argument that the left side is a function of t, but the right side that says there is no dependence on t. So what can it be if a function is a function of t but it doesn't depend on t? It means it's a constant function, and therefore we set that constant as negative lambda. We choose negative lambda as this constant because then this becomes this well-recognized 1, which is actually same, along with this, it's same as the step 1's solution. Okay, and also make sure that along the way you write that if t equal to 0, then that forces this to be equal to 0, and that forces u to be exactly 0, but that's trivial, that's not good. So you end up saying that these boundary conditions are what you need, and that's exactly what we solved in step 1. So we use the step 1 result to write this down, and then hence we find that uxt must be this, with n being 0, not 0, but 1, 2, 3, and so on and so on. Okay. And now step 3, what you do is, since that's the solution, now you can take the linear combinations of it. We start from n equals to 1 because n starts from 1. If we found that n equal to 0 was indeed the eigenvalue, then this summation should be modified. You should put c0 plus cn like this, but we know that n equal to 0 didn't give us any eigenvalues or eigenfunctions, so that's left out. N starts from 1. So I simply took this and added them up. Okay, now we use the fact that ux comma 0 is given. It was 3x squared, I believe. What was it? 3x squared, right? So this is 3x squared, and if you plug in 0 here, e to 0th power is 1, so we end up with this equal to this, which means we're looking for the Fourier sine series of this function, okay? With cn's actually being same as the bn, whose formula is the Fourier sine series 2 over L, 0 to L, the function f of x times sine of n pi over L times x dx. Okay. Alright, so we calculate bn according to that formula. We know that the length L is 2 here because this is 2. And then the usual integration by parts with tabular. So you do d integral plus minus with 3x squared here, and then sine n pi over 2x here. And this is 6x, this is 6 and 0, so you have to put 3 more here, plus minus, and if you do all that, this horrible thing is the integral that you get, and you plug in the endpoints, and using the fact that sine n pi is 0 and cosine n pi is negative 1 to the nth power, you can find all the values like this, and this is your answer. Okay, so that's your Cn. You find your Cn by that. So you can go back and plug it into your formula here. Cn is known, and what do you get? That means uxt and Cn is known, and therefore you have the solution uxt. That's it. That's the full solution. And of course, this could be divided into many parts. For example, I could ask find the sine series of 3x squared in a different question. I could ask the endpoint value, eigenvalue, eigenfunction question. And then I could put this as the next question, which will use what you've obtained in the previous one. Okay? So you have to know every part of this solution because it is possible that the entire thing could be on the final exam.